Hello students, today we will discuss more about Poisson bracket formalism. Particularly in this session, we will see what are the Poisson bracket relations between the components of linear and that of angular momentum. So as per the definition of angular momentum, you know the angular momentum J is given by vector product of or cross product of radial vector and the linear momentum. So R cross P. So that is given by R in vector terms. You can see it is given as x I cap plus y j cap plus z k cap. It is taken cross product with linear momentum component in vector form, that is px I cap. Then you have py j cap plus pz k cap. So if you do the cross product, what you get will be I cap into y into pz minus z into py as first term minus j into x into pz minus z into px plus k component will be x into x into py minus y into px. Okay, so making the second term also a positive term, you can write it as negative can be taken inside, so it becomes z px minus x pz. Okay, so when you compare it with the components in the LHS, you can see jx is having component as y pz minus z py, and jy is having component as z px minus x pz, and jz can be equated to x py minus y px. Okay, so these are the components of angular momentum along x, y and z direction, which has been written in terms of coordinate and momentum. So the one thing you can see from here is that the jx component doesn't have any dependence on either x component nor the px component. Okay, similarly jy component do not have any dependence on y component, y coordinate or py coordinate, py momentum. And similarly jz doesn't have any dependence on z coordinate or pz momentum. So that will be helpful in a later discussions. So let us first write down what are the relations between components of linear momentum. That is already known from the fundamental Poisson bracket itself. You already know if you take the Poisson bracket of momentum component with any other component or with itself, it would be 0. So that is already known. And the second relation we are going to see is between the components of linear momentum and that of angular momentum. So let us write the first one. So jx px. So in this calculation we need to keep in mind that if you take Poisson bracket of any function with the momentum component, we will be getting the different, which is same as differential of the function with respect to the coordinate. Okay, so making use of that concept, you can write jx as a function is taken Poisson bracket with px. So what would be that? The derivative of jx with respect to corresponding coordinate. What is the corresponding coordinate of px? X. Okay, and it is evident from the relation that there are no x component, x coordinate in the jx component, so the differential would be 0. Okay, similarly you can write jx and py. So as per the relation you can write it is the variation of jx with respect to the corresponding coordinate, that is y. So in jx you have y component, y is present, so the differential of that is given by pz. So we can write it as pz. Next one, jx with pz. So it would be differential of jx with respect to the coordinate of pz, that is z. So z is available in the relation. So when we differentiate jx with respect to z, it would be minus py. So here you have minus p. So every time you have to keep in mind that if you make Poisson bracket of an angular momentum component with the corresponding linear momentum component, then it would be 0. Why? Because jx component doesn't have any dependence on corresponding coordinate or corresponding linear momentum component. Okay. Similarly, you can do it for jy px, which would be differential of jy with respect to corresponding coordinate is x. So in jy, x is present, so it is minus pz would be the differential. So that is written over here. Similarly, jy with py would be dou differential of jy with respect to corresponding coordinate, that is y. And you know, in jy there won't be any coordinate, there won't be any y dependence, so it would be 0. In jy with pz, you can write it as differential of jy with respect to the corresponding coordinate, that is z. So z is present, so the differential would be px. So that is given here. Similarly, you can do it with jz px, jz py, and jz pz, which is equal to 0. Okay, now coming back to the next case. So far we know what are jx, jy, and jz. Now we'll write down what is the relation between components of angular momentum, Poisson bracket relation. So let us take the first, consider jx and jy. So we can make use of the definition of Poisson bracket. So here you can write 3 components are available. So you'll have 3 such terms. So what is that? Dou jx by dou x, differential of jy with respect to px, and you have to invert this. So it would be minus dou jx by dou px, then dou jy by dou x. Similarly, you have to do for y py and z pz. So these are according to the definition of the Poisson bracket. Now you have to evaluate. So let us see, what is jx by the differential of jx with respect to x? There are no x term present in jx, so it is 0. So this term becomes 0. Okay, and what about this jx with respect to px? Here also there are no component of px in jx, so that term also becomes 0. Next one here, jx with y and jy with py. So here also similar components are taking up the differentials. So in jy there are no component of py, so it is 0. So look for any differentials which have similar components, so that would go to 0. So you can check here, yeah, y and y is coming, jy and y is coming up, so there are no y present here, so the differential will be 0. But for the last term here you can see jx is taken differential with z, so with respect to z it would be minus py, that is written here, and jy with respect to pz, jy with respect to pz is minus x. Okay, fine, minus jx with respect to pz, so it is y, into jy with respect to z, that is px. So px is written here, so this become positive, so you can write it as xpy minus ypx. So what is xpy minus ypx? Yeah, here it is evident, it is jz. So you have the relation, if you take Poisson bracket of jx and jy, then you'll get jz. Okay, so the similar way you can do it for other components also, and you'll get, and it is easier to remember what are the relations also. It comes in the cyclic permutation, so that is, if it is between jx and jy, you will get jz. Then cyclic order you have to take, if jy and jz, you'll get x. If jz and jx, you'll get y. So here you can remember the order of x, y and z. So you have to take in order in order to get positive quantity. So this and this Poisson bracket of jx and jy will give z component, then y and z will give the x component, then z and x will give, that is the correct order, the z and x will give the y component. In all other order it would be negative. So all these you can prove yourself. And let us check a remark that the components of angular momentum are conserved in a central force potential. So we are considering a particle which is moving in a central force potential. For a central force potential, the potential will depend only on r. Okay, so here r is given as square root of x square plus y square plus z square, which is the distance from the origin. Okay, that is, we are considering a point in 3 dimension. So it will have the x value, x distance from the origin, and you have y distance from the y distance as well as the z distance. So the total radial vector will be given by square root of x square plus y square plus z square, the magnitude of the radial vector or the distance from the origin. So you have Hamiltonian as kinetic energy plus potential energy. So kinetic energy for a particle is given as p square, linear momentum square, divided by 2m. So similarly, px square by 2m plus py square by 2m plus pz square by 2m plus potential. Now we are going to check the first component, that is jz, and you know what is jz, and it is easier to remember also. Here also cyclic permutation can be taken up. So jz can be written as x. First you have to write the coordinate. So x followed by the momentum in this order. So xpy minus inverted. So it is ypx. Similarly, you can write jx, which would be cyclic order. You have to take y, then momentum of the other component, that is ypz minus, then you have to just invert this, so that is zpy. Okay, so in this way also you can keep it in your memory, and jy can be similarly written. So after y you will get z in the cyclic order. So z, then comes x, so px minus, then the inverse of this, that is x, and pz. Okay, so in that way you can remember this relation. So let us take jz first, that is xpx py minus ypx. So first we write down, not to check whether it is conserved, that is constant of motion, you can write it as Poisson bracket of jz with respect to h has to be 0. And what is h? H is kinetic energy plus potential energy. So you can, according to the linearity, you can write it down as jz taken Poisson bracket with t plus v is same as taking the Poisson bracket of jz with t plus jz with v. So we can individually evaluate these two Poisson brackets. So taking the first term, that is the Poisson bracket of jz with kinetic energy, you can write down as per the relation of definition of Poisson bracket. You have with respect to x and px plus with respect to y and py, then with respect to z and pz. But you have to keep in mind, only the non-zero terms are those which doesn't have any that means you can omit these terms. Why? because the kinetic energy doesn't have dependence on the coordinate. So these terms will be 0. The variation of kinetic energy with respect to coordinate, those terms are 0. Okay, and so the only non-zero terms are Jz, the first term, second term, and what about the third term? Third term is also 0 because there involves the differential of Jz with respect to z, and you know in Jz there are no presence of z, so that will also goes to 0. So there are only 2 terms present. So now you can write down what are now you can write down what is it, Jz. So what is Jz? Jz has been written as, in cyclic order it would be x into py minus y into px. So differentiating Jz with respect to x, you will get it as py into, then kinetic energy is differentiated with respect to px, so the only term is px square by 2m is there, so differentiating that you will get it as px by m, that is here. Okay, then you have Jz is differentiated with y, so you'll get minus px, so that is coming here. Then kinetic energy is differentiated with py, so similar to this term you will get it as py by m. Okay, because you have the term present as py square, that is the only dependent term on py, so differentiating that you will get py by m. Okay, so here you can see these two are the similar terms, so on subtraction they will cancel out. And similarly you can do it for potential also. So when you take the Poisson bracket with potential, you can write down the definition of Poisson bracket. So you have to take Jz with respect to x and potential with respect to px, and just reverse the order, then with respect to y and py, and with respect to z and pz. Now as we mentioned earlier, potential is dependent only on the coordinate, so you can omit those words because they are 0. Dou v by dou px, dou v by dou py, and dou v by dou pz terms are 0. So the only non-zero terms are this one, and what about this? Here there is a differential of Jz with respect to pz, and you already know there are no presence of pz in the Jz. Okay, so that will goes to 0. So now you can again so now you can see what is dou Jz with respect to px. So dou Jz is given by minus y, and minus become plus, so it is plus y. Then dou v by dou x is written as such, and then you have minus Jz is taken differential with py, so py you will get x, so x into dou v by dou y is written as such. Now you know the potential is depend upon r, so we can write it as using the chain rule, that is v is dependent upon square root of x square plus y square plus z square. So the differential of that could be written as 1 by root of x square plus y square plus z square. Then you have differential of x, so it will become 2x. So the 2 and 2 will cancel off. So remaining is x into x divided by square root of x square plus y square plus z square into the differential of v with respect to r. Similarly, you can write dou v by dou y is same as y divided by square root of x square plus y square plus z square into differential of v with respect to r. Okay, v differential. And substituting these back, you will get x into, so dou v by dou x. So here you have already y present, then you get an x over there, then square root term is there, then v prime of r minus, from here you have an x here, then from dou v by dou y you will have a y over there, then divided by square root term is there, then you have v prime of r. So these two terms are the same, so that will also lead to 0. So now you have proved that both the terms are going to 0, so which means Jz Poisson bracket with Hamiltonian is 0, which implies the Jz, z component of angular momentum is conserved. Similarly, you can do it for jy and jx. Okay, so that ends our portion on Poisson bracket. So we have seen canonical invariance of Poisson bracket, giving it as a tool for checking whether the transformations are canonical, and you can make use of fundamental Poisson bracket in that aspect. And we can also check whether the functions are constants of motion using Poisson bracket. Okay, thank you.